Okay, good morning, everyone. I'm going to present the discovery new low temperature star Abrondo was in the photometric surveys, presented as a Star Lab 2021 as part of the program Enlace for the Project 7. The participants are CG, Adriana, Eduardo, Aranza, and Dr. Adam Burgatzer as a mentor. Yes. We recall that star is a stellar object that is sufficiently massive to generate a fusion process in its core due to the gravitational pressure inside the object itself. A brown dwarf is a substellar object. It's not massive enough to fuse hydrogen. Usually, there has a mass between 13 and 18 mass Jupiters. The brown dwarfs are also known as ultra-cold dwarfs. You see this. And in this figure, we can see a relative size of a brown dwarf. These are also known as a figure star. The astronomers use the spectral types to classify the stars according to the relative surface temperatures, and specifically for the brown dwarfs, we have the types M, L, T, and Y. The brown dwarfs are hard to find. An interesting aspect of these brown dwarfs is that there are planetary system around them. It is the case of a TRAPPIST-1 system that has been detected terrestrial worlds sizes. So we want to find more brown dwarfs, but they are hard to find. Therefore, the main issue in this project is to identify and classify ultra-cold dwarfs, UCDs, and not ultra-cold dwarfs in deep multiband photometric surveys. To do so, we are going to use the random forest model that is a machine learning technique to solve complex problems. We use an ensemble of decision classifiers where the trees are trained. Each tree in the forest is trained with a bootstrapped version of the original training data. A good thing of this method is that we can analyze a big set of data quickly. And in our next slide,
I am CJ. I'm going to talk about the method we use in our survey. A supervised learning method or random forest. First, we created two different datasets called SkillSpec 2016 and BEST 2018, based on several astronomical survey data. Each dataset with different point sources of the sky, so we could have different results and compare our random forest models. The dataset contained principally photometric data in A bands, which were subtracted to make corals. Then we built a random forest classification based on these corals to classify our sources as either ultra-cool dwarfs, UCDs, or non-ultra-cool dwarfs, non-UCDs. To verify the UCDs that were predicted, we built a random forest classification and regression to predict the spectral type of each source and compare it to the data in the astronomical database. To see how good our random forests are, we check the accuracy score. Our goal is to get as close to 100% as possible. Next slide, please. To achieve this goal, we use some parameters in our random forest models. We set up numbers of trees, random state, and cross weights. We also took 75 to 90% of our data to split into a training set that will train our models, then a validation set to adjust the parameters, and a test set to evaluate the generalization of our models. By this way, we ensure that our models are not overfitted and will fit good on unseen data. We also use an actual versus predicted graph to see our model's performance. We can see this graph here on the left, where the x-axis is the actual spectral type, the y-axis the predicted spectral type, and the points are predictions. The diagonal line represents a perfect predictions. Therefore, the closer the points are to the line, the more accurate the prediction is. Furthermore, my teammate will talk about the results that we obtained.
Good morning, I'm Eduardo and I will be presenting our results. First, I'm going to talk about the results when we use the random forest model to classify whether the source is or not a UCD. On the right side of the slide, we're showing a confusion matrix, which tells us how many sources were correctly classified. On the x-axis are the predicted labels, and on the y-axis are the true labels. The numbers inside of the confusion matrix show the amount of sources corresponding to each section, which can be also seen by the background color for that region. We can see that only 10 sources out of about 1,200 were misclassified. It should also be said that we got an accuracy of 99%, which means that most of the sources were correctly classified. Next slide, please. Now I'm going to talk about the results using each data set to get the spectral types of the sources. The plots in the right side of the slide are showing the importance of each feature we used in our model, which are the colors that we got from the sources. The upper right one is from the best 2018 sample, and the down right one is from the SCIRSPEC 2016 sample. The higher the bar, the more important the feature is. With these plots, we know which colors are most relevant to get a better classification. More specifically, for the best 2018 sample, which had around 9,300 sources, we got an accuracy of 97%. Our most important feature was C-Y, which is a color, and the average classification error was of 0.43 subtypes. On the other side, when working with the SCIRSPEC sample, which had 233 sources, we got an accuracy of 97%. Our most important feature was W1 minus W2, which again is a color, and the average classification error was of 1.32 subtypes.
Hi, I'm Aranza, and I will be presenting how we put the random forest models we built to the test. To put these models to the test, we extracted 2 random samples from different coordinates in the sky. In the first sample, 99.14% of our sources were classified as non-UCDs, and 0.86% of the sources were classified as DCDs. On the bottom, we can see a graph showing this distribution. On the y-axis, the frequency, and on the x-axis, the labels, either labeled as non-UCDs or UCDs, and if they're labeled as UCDs, further divided into their subtype groupings based on spectral type. The second sample ended up being much smaller, and because of this, it was 99.99% of sources that were classified as non-UCDs, and only 0.00135% of sources were classified as DCDs. On the bottom, we once again have the same type of graph showing the distribution for this sample. Next slide, please. So after making these predictions, we used the astronomical database SIMBAD to check how accurate some of these were. The source on the right is one that was predicted perfectly. So it had it was a UCD, and the predicted spectral type was the actual spectral type. And this shows that our model was indeed pretty accurate. Then for the second source was one we found interesting because our model classified it as a UCD, and SIMBAD classified it as a brown dwarf candidate, meaning that it was thought to maybe be a brown dwarf or UCD, but it wasn't confirmed. Next slide, please. So the key outcomes of our projects ended up being that we were able to train a successful random forest model with which we were able to identify UCDs and discover ones that weren't fully identified before. And then we also concluded that machine learning was indeed an efficient method for dealing with large data sets, like in this case, astronomical research, because this type of research always takes out really large data sets, and going through each source one by one is extremely hard. So this type of method is really helpful to find how we get UCDs and classify them. Next slide, please. And last but not least, we would like to express our thanks to Dr. Olivia Grave, Professor Adam Bergasser, and our graduate mentors, Roman, Dino, Christian, and Chris. Next slide. And thank you, our audience, for your attention.
Great. Move on. Project 8.